I posted an assignment last night on Skype. Sorry. I'm sorry, I have to catch my breath. There are three simple problems, but I will have a grader to help me with the grading once I get your papers. So I'm looking for creative ideas on how to take care of this. One possibility is I grade a sample, I post a solution. The other one is that some of you may volunteer to be GTAs for one day, occasionally. So you can grade the class papers. But in this case, your submission should be kind of hidden identity kind of thing, so maybe the best thing in either case for now is when you submit your paper, not to write your name on it, just the last few digits of the student ID number until we figure out how we are going to go. After the solution, after the papers are sent in, I will post a solution on Scholar site. Okay. We started talking about a situation when we have waves traveling both directions. And we wrote the general solution for this case. Just a drink of water, so catch my breath here. Okay, so we are looking at the general solution, which involves having both B plus and B minus. That means on our line, there are two waves traveling in the two directions. The B plus wave and the B minus wave. And we said if I were to look at V of Z magnitude, we notice that it will have places where the two phasors add up and places where the phasors subtract. So this is where V plus and V minus line up with each other. The two phasors line up, and this is where they go in opposite directions. So the V plus magnitude minus V minus magnitude. I should write magnitude of all that in case of one of them is greater than the other. Still, I'm showing magnitude here, so it should be that way. So actually, we're showing the analogy of the two phasors, the two pieces of chalk, if you remember. We said if I were to ignore the phases, or just look for a point at which they will align anyway, and then with time, which means position as well, this phasor moves in one direction and the other phasor moves in the other direction. All right? until there comes a point where the two phasors are completely opposite to each other, and that's where they subtract. And then the continuous process will imply that they will be both negatives, but in magnitude they will show us positive. So phase-wise, if this is a complete alignment in the 0 phase, this is a 90-degree phase, and this will be a 180-degree phase, and the process will continue to repeat, 180, and then that will continue to repeat. If we were to look at the distance, this is position distance. If we look at the distance at which this happens, now in this process here we ignore the alpha, if you remember, right? We ignore the magnitude changes. Otherwise, if the magnitude were to change because of attenuation, then it's not going to be the same magnitude. It's going to be doing something like this. Right? The magnitudes are going to be changing constantly. But this here is the lossless case. Obviously, that's not a simple thing to derive, and that's why we are putting it away. Losses will do that. Either low loss or lossy line, they will do that kind of thing. We're putting this away because we want to get to the physics, so we're focused on the simple case. Sometimes if you look at the whole picture, it gets so complicated you won't be able to extract physical insight. So we look at the simple case of the lossless line. For the lossless line, it means there is no alpha, so this is actually v plus e to the minus j beta z plus v minus e to the plus j beta z. And as you can see, you can play games with this one here to derive this expression. And one way to do it is to add v plus, actually, let me cheat here. What do we add and subtract? Oh, okay. I'm doing it in the time domain. That's why the addition and the subtraction was simple. That we can also do it in the frequency. Right. We add a v minus e to the minus j beta z and subtract the same thing. Okay. By adding and subtracting the same quantity, obviously we haven't done anything. Now I combine these two together. And combine these two together. So you end up with v plus v minus e to the minus j beta z. I'm sorry, like that. And then you have a v minus, and then you have e to the plus j beta z plus or minus e to the minus j beta z. Now this one here is cosine beta z minus j beta z, or plus j beta z, and this one here is cosine minus j sine. So this comes out to be 2v minus sine beta z, right? Cosine plus j beta, there is a j. This is cosine plus j sine, and that's another cosine plus another j sine, so you end up with 2j v minus sine beta z. And this one here is v plus v minus e to the minus j beta z. So as you can see that this one here is a traveling wave of the intensity of v plus v minus. That's the traveling wave. Well, this one here is what we call a standing wave. Why do we call it standing wave? Let's convert both of these to the time domain, and you will see. Convert this part to the time domain, then there was v plus v minus, and then you have cosine omega t minus beta z, right? Which is, as we saw before, is a wave that travels with time. This one here is it's the first time I interact in the frequency domain. This part I always do in the time domain, and that's why I hesitated for a moment there. I saw something different, and sure enough, I was doing it in the frequency domain instead. Let's look at this part here. So what do? You end up with 2j v minus sine beta z, and multiply by e to the j omega t, and take the real part. Well, here you end up with cosine omega t plus j sine omega t. And when we take the real part, the j and the j gives you the real part here. So end up with 2 v minus magnitude sine beta z sine omega t. That's what you end up with. That's the time domain part. So this one here converts to 2 v minus magnitude sine beta z sine omega t. Right? So that's the conversion of this. That gives you v of z and t. It's giving you a travel wave. This is what we saw before. That goes with omega over beta as a phase velocity, and the wavelength is beta, 2 pi over beta, which is lambda. Same thing that we thought before, it's just a different amplitude now. It's a v plus v minus. That's your traveling wave. The standing wave part now, let's try to map that, because we haven't seen that before. We've played this game here, but we didn't do this one. You have a sine beta z. So with z, it goes like a sine, but multiplied by sine omega t. And as t changes, that number here is going to change, but it's not going to change the waveform. It's going to change the amplitude, because that's really a multiplier of this. So as a multiplier, it will be a fraction. It could be a 0. It could go negative. But it will never change the 0 once you get a 0 here. If you have a 0 here because of sine beta z is equal to 0, that's never going to change it. The 0 here is going to stay a 0. But if this is a 1, and this is a 1, you get a 1. If this is a 1 and that's a half, you get a half. 1 and 0, you get a 0, and so on. So the magnitude or the amplitude is going to change, while the zeros of the original function here are never going to change. That kind of wave is called a standing wave, because it doesn't travel. This one here, the phase constantly shifts. Here, your nulls are always in the same location, determined by this part. looking at the way I played the game, I think it would have been better. Like I said, I never done it before in the frequency. It's the first time to do it in front of you guys here. So I think I should have combined things differently to arrive at the easier form. This form here is okay, but there was an easier form that would have come by combining this and that. Not the way I done it. This combination and this combination would have arrived at an easier form. But anyway, the point is, I got myself a solution now that consists of a superposition of, if I do magnitude now, the V magnitude of this is constant, right? The magnitude is constant here. And this one here is, so you have a constant magnitude here, and superimposed on it, the magnitude of this is going to be, let's do magnitudes here. Magnitudes will be like this, right? No negatives, you fold everything up. And time doesn't play a factor here because I'm talking about the magnitude of the phase. So the magnitude of that's constant, and the magnitude of this is sinusoid. So that's what you end up with. So this is really the picture that we're seeing here. It's an approximation here in the picture, because when you do things properly, you don't get those sharp nulls unless you are talking about zero. Only the case where this constant or this traveling part is zero that you get good nulls. But if you are up here, usually those are rounded. The full mathematical solution obviously can reveal all that. So the point is, the general case that we're talking about has two parts: traveling wave and a standing wave. This one here would be when the traveling wave is zero, you have a pure standing wave. You have a pure standing wave. Any questions so far? So when we have the general case, usually we try to jump to a different presentation that is more convenient to work with rather than the V plus and V minus. Working with the V plus and V minus is usually troublesome. Can't carry it too far. So what we do instead is take the V plus e to the minus gamma z as a coefficient out, and we would be left with 1 plus V minus over V plus e to the 2 gamma z. And we'll call this quantity here gamma of z. So the definition of gamma of z is the ratio between the wave traveling to the left over the wave traveling to the right. V minus e to the plus gamma z divided by V plus e to the minus gamma z. This presentation is almost the standard that everyone likes to work with because it brings in a very important and significant physical meaning of the reflection coefficient. Because, like we said here initially, remember we only had one source on the left. We didn't have a source here. So this wave here would come as a result of a reflection from the termination at the far end. Okay? Obviously, if there is another source there, the labeling of reflection coefficient would be kind of inaccurate, because the wave coming back would be partially because of the other source and because of the reflection. All right? But in case of one source, this labeling here brings in that physical insight. That's the reflection between so it's a negative wave divided by the positive wave. All right? That's the definition of that. It's obvious that that reflection coefficient is functional position. Right? Z is effective. V plus and V minus are constants, right? We mentioned that several times. But different locations will have a different reflection coefficient. So we specify a few locations, gamma of 0, for example, that's the reflection coefficient at the input side of the line, is V minus or V plus. Gamma of L, which is the reflection coefficient right at the far end of the line, is going to be V minus e to the plus gamma L divided by V plus e to the minus gamma L. Another useful relationship is what is gamma of Z at some location in terms of gamma of Z at some other location. That would be e to the 2 gamma Z2 minus Z1. So in other words, if I know the reflection coefficient at some location on the line, I can get it at the other locations. If I know it at the load, if I know it at the input side, if I know it at Z1, I can get it at any other location. There is that nice and useful relationship.
What happened to the V minus and V plus? What happened to the V minus and V plus?
They ratio out. The same V minus or V plus in gamma Z1, V minus or V plus in gamma Z2, they ratio out. Right? And you end up with, where is it? There it is, all right? That's gamma of Z. Look at this form here. That's a constant times that. You put it at Z1, you get that. Put it at Z2, you get that. So the ratio between the two, this one cancels, and you have that problem. Okay? So from this, I kind of reduced my unknowns now to gamma of Z and V plus. Right? I used to have two unknowns, V plus and V minus. And I needed to bind the conditions together. I still have two unknowns. V plus now and gamma of Z. Gamma of Z is a complicated unknown, which is actually, this is the only part of unknown in it, which is actually what? Gamma of 0. So now, my two unknowns, this is V plus and V minus, have converted into a V plus and gamma of 0. Or gamma of L. Right? If I know this or that, plus V plus, I have my two unknowns. Right? Okay, that's good. One more thing we do. All these are mathematical games that we play that eventually are going to make the solution of the general case much nicer, much simpler. We write the I of Z. We can never get the full solution before we write the I of Z as well. That's V plus e to the minus gamma Z minus V minus e to the plus gamma Z over Z naught. So I do the same thing. So it becomes V plus e to the minus gamma Z over Z naught 1 minus gamma of Z. And if I divide V of Z over I of Z, which we call the impedance at any location, Z of Z, that's what we call the driving point impedance. The driving point impedance is the ratio of the voltage over the current at any location on the line. That would be equal to, you take the ratio, you end up with Z naught times 1 plus gamma of Z divided by 1 minus gamma of Z. So here I add this relationship to the kind of relationships we had. So Z of 0 is equal to what? Z naught 1 plus gamma of 0 1 minus gamma of 0. And Z of L, I'm going to write it here, is equal to Z naught 1 plus gamma of L 1 minus gamma of L. Trying to get familiar with this gamma thing, right? By writing it in so many forms. So guess what? Gamma of 0 is related to Z of 0. So this one here is directly related to Z of 0. And this one here is directly related to Z of L. So again, my two unknowns were V plus and V minus. Now they have become V plus and any of these four. Right? Any of these four will do. So these are equivalent to V plus and any of the four terms. Either gamma of 0, gamma of L, Z of 0, Z of L. The relationships are simple here. We can get them in terms of each other. Obviously, the nicest combination would be this one and this one. Why? Because Z of L is the impedance at the end of the line, which is your termination, which we should be familiar with. So, with that in mind, if I go back to my transmission line, we said we have a source here, Vs and Zs, and I have a ZL here. V of L, sorry. The ratio between V of L over I of L, which is Z of L, is equal to Z sub L. Right? So, knowing Z sub L is easy. That's a given for our problem. So our solution for the unknowns is now reduced into only one unknown. By playing all these games here, we reduced the math that we need to do to only one boundary condition at the input side. Because this boundary condition is so simple, Z of L is equal to ZL, and it's right there. And if I know Z of L, I can put it here. I can get gamma of L. If I know gamma of L, I can get, where is it? gamma of L, I can get V minus over V plus, right? And I know V plus, that means I know V minus. So we can summarize that. On the side here. So ZL, and then gamma of L would be what? Based on this one here. Is equal to ZL minus Z naught divided by ZL plus Z naught. That's what you do if you reduce this. If you flip this around, you get that. So I got my gamma of L. Now I can get V minus or V plus as gamma of L times e to the minus 2 gamma L. So step 1, 2, 3, I get V minus over V plus. That's not much manipulation, it's a straightforward math. Now to get the second boundary condition, which is right here, number 1. Let me label this as boundary condition number 2. Do boundary condition number 1. V of 0 is right there. I of 0 is right there. And I can write an equation here, Vs minus I of 0 times Zs is equal to V of 0, right? That's your KVL around the input side of the line. V of 0 is V plus V minus. And I of 0 is V plus minus V minus over Z naught times Zs. If I take V plus as a coefficient, Vs minus V plus Zs over Z naught, 1 minus V minus over V plus, which is gamma of 0, if you wish. Is equal to V plus times 1 plus gamma of 0. Do I know gamma of 0? If I know gamma of L, I know gamma of 0. Because gamma of L and gamma of 0 are related to each other here, right there. So I replace gamma of 0, which is right there, that's gamma of 0. So it's equal to gamma of L e to the minus 2 gamma L. So this one here is gamma of L e to the minus 2 gamma L. Gamma of L e to the minus 2 gamma L. This is now one equation in V plus. Because gamma of L is right there. Well, as it turned out that obtaining V plus is cumbersome. The equation is very involved in nice, not nice looking at all. And actually that is, the expression for that is on page 17 of the chapter. You know, you can see the equation is not that simple. But anyway, as it turned out that V plus, the determination of V plus is not really the thrust of dealing with transmission lines, because that's only an indication of how much power is going down there. And how much power is going down there is important, but it's not really the main issue. The main issue usually is how much reflection is happening there. And as you can see, the gammas, or the reflection, is happening because of the impedance mismatches. If you were to terminate the line in a Z0, the characteristic impedance, then your gamma of L would be 0, and if gamma L is 0, that means V minus over V plus is 0, that means gamma of Z is 0, that means all the gammas are 0. That's really the main issue that we struggle with in transmission line systems, impedance matching. If the signal decays, we can always boost it. We can always pump a bit more power. All right? We can have some repeater somewhere to make it live again. But if it gets distorted, it's harder to clean. If you have reflections and you have interference and you have all these things, the issues are much more serious. So the issue of getting V plus is there, yes. It's just one complicated equation. We can program it and get it out of the way. The main issue is going to be, how can we get rid of gamma?